Thank you for joining our Integrated Building Design seminar. My name is Joros Petru. I'm a research fellow in building physics and urban modeling at UCL ID, and I'll be chairing this webinar. In this series of webinars, our speakers present state-of-the-art case studies of integrated architectural, environmental, and structural design. In case you have missed our previous webinars or would like to watch them, you can find most of them on YouTube. Today, we have three excellent speakers that will present on the challenges and insights from designing and building a world-class lab at the University of Oxford. Shane Mellon from Hoare Lea was the lead mechanical engineer on the scheme. Shane joined Hoare Lea as a graduate in 2009 and is a core member of the Hoare Lea science and research team. He has worked on projects ranging from higher education and commercial science to deep tech specialist laboratories and clean room facilities. Shane strives to better understand how we use buildings and develop designs in a way that centers around the user experience and how the building can work best for them in their day-to-day activities. Alex Young, associate at Hawkins Brown Architects, was the lead architect on the scheme. Alex joined Hawkins Brown team in 2016, and he has a wealth of experience in the design and delivery of buildings for education. He has designed buildings for primary, special needs, and high technical higher education facilities and has worked at all scales. Finally, Paul Matthews was project technical lead from Laing. Paul's role was technical lead for the contractor on the scheme, and having worked as a mechanical engineer for RUP previously, Paul has an excellent appreciation of the challenges faced by designers and contractors alike, and is currently part of the leadership team delivering the Stephen A. Schwarzman Center for the Humanities at University of Oxford. Before we begin, I would like to ask our attendees to share their questions with the speakers through the Q&A function, and the speakers will try to answer your questions during and at the end of the presentation. I'm now happy to hand over to Shane.
Excellent. Well, good afternoon. Thank you for that, Joris. Welcome to everyone for taking the time out of your afternoon to come and listen to us speak. Hopefully it'll be an interesting event. So if we just jump on, with obviously introductions, we've covered them with just a couple of boy band pictures here, just as who we are as individuals, to be able to recognize the faces. And in essence, yeah, we just thought we'd start off with what we hope you should be able to gain from today. So obviously biochemistry completion, or biochemistry phase 2, is also known as the kind of key project we're going to work through. Hopefully we're going to give you a good, decent overview of the project and the kind of key features and the interesting aspects of that. Also as part of that, kind of key challenges we face and how we can approach those problems and overcome them as a collective group. We're also going to kind of delve in a little bit on kind of a DFMA, which is design for manufacturing assembly. So it's I wouldn't say new, it's been around a while, but it's certainly something that was applied in a very effective manner on this project. And so I think certainly something we're very keen to share. And then I suppose at the very tail end of that, we're going to share what we learned as individuals on this journey. And so, it's as much as we all know together, there's always things you learn. Every day is a school day. So, we'll be keen to share that with you guys. So a little bit on the housekeeping. So obviously the session's circa 1 hour long. We're aiming to keep our presentation to about 45 minutes to allow a little bit of time for Q&A. That may vary depending on the nature of how it runs, but we just thought we'd show you how we're setting that out. As was mentioned there in the intro, very keen for you guys to engage with any questions as we go. We're keen to have an interactive discussion, or alternative, if you want the questions at the end, not a problem either. But yeah, we just thought we'd show that. Okay, so we jump straight in on the project. So the project itself is actually biochemistry completion, or biochemistry phase 2. It's a kind of a multifunction science building in the center of the science area within the University of Oxford. Circa 73 million construction costs, so it's a decent sized project. Finished around December 2020. And the collective team members, as you can see, are listed there, but obviously ourselves, Hawkins Brown, and obviously Laing work on the construction side as part of the team on the call today. In terms of scale, it's about 13,000 square meters. I suppose by way of reference, if your typical average house is about 100 square meters, you can get a sense of scale of what that is. It's a big building, and it's arranged over 2 levels of basement and 4 above ground floor levels, excluding plant. There's no plant level on top of that. The brief, we'll come into the brief in detail, but in essence, a lab hotel. Literally, they weren't sure who was going to move in. It needed to be very flexible and adaptable to cater for a multi-range of different kind of research and specialist groups. There isn't teaching in the building. It's primarily a research facility, but yeah, still very flexible and adaptable. That was the core brief. So if we jump into the building layout, I think something that we're keen to highlight was the fact that actually our part, as I touched on, was phase 2. There is a phase 1 building that was built circa 2008, 2009, and Alex, I think, is just going to add a little bit more detail on that.
Yeah, so basically, just to explain the colours, The yellow areas are the write-up, the light blue are the primary labs, and the dark blue are the secondary, more specialist labs. The rooms that are in orange are just the offices, and the purple spaces are the meeting rooms. The one thing that you'll note that is in phase 1, the primary labs are positioned on the outside of the building. But as we started to design phase 2, which was about 10 years later, we tried a lot harder to get the net to gross ratio working a lot harder, which meant that one of the ways in which we could achieve that was to actually push the right up to the outside of the building, which is no bad thing, because obviously those right up areas then get to they get a lot more daylight. But what it meant is we could reduce the amount of circulation down, which meant that generally they could get a lot more lab space, which was part of our, that was a very defined brief that we got from the university at the time. So next slide, Shane. And that is just another image, albeit isometric, so you can sort of see the build-up between phase 1 and phase 2. And that is an image that is looking specifically at phase 2, and that gives you a bit of an idea as to how the amount of furniture and the amount of lab benches and potentially the amount of researchers who will be working in this building. This is a section through the building, and it gives you some idea as to the different space types. If we start from the top, which is what you can see as a large screen, that is where the plant is. Now from lower ground, from third all the way down to lower ground is where you have your typical generic wet lab spaces with the perimeter right up. And in the basement is where we had more of the service heavy centralized facilities, such as the glass wash, the server rooms, and also lots of the very environmentally sensitive lab spaces, the specialist lab spaces, such as the laser labs. And also we had a cryogenic electron microscope suite down there that will be containing 3 electron microscopes that have really, they're very highly sensitive, and you have to meet very high environmental criteria and vibration criteria. So by far and away, we could put those down in the basement where they were much less likely to be affected by external vibration, for example. The one thing I would say about the electron microscope room is it was also very, very sensitive to EM radiation. So that was the best place for it to go, where we could actually put in features to actually help cancel out the EM radiation that may affect those particular microscopes. Yeah,
so that's electromagnetic interference. So things like anything with like a ferrous material and a moving part, like a motor or a lift shaft moving up and down, or a lift, they're the kind of things that influence that. So all of that had to get built into the consideration and the space planning for the building that Alex just touched on there. So that's hopefully that gives you a good flavor of what that looks like. If we then move on to the next stage. So perhaps, Paul, is this one that, or maybe I can do a quick intro. So this, some of you may be familiar with this. So this is the Royal Institute of British Architecture kind of plan of works, which pretty much all built environment projects adopt and follow. Obviously starting with stage 0, it's a strategic definition where the client basically decides they want to have a building of sorts. The kind of main design team gets mobilized at either stage 1 or stage 2. In the case of Biochem, it was stage 2 onwards. So we as a collective design team came together at stage 2. We went through each milestone, which is stage 2 is obviously concept design, so fairly high level. Stage 3 is develop, so a bit more detail, and then technical design, stage 4. That's your kind of the final point at which we go out to tender. And it was at that point that Laing were approached and were part of the tendering process. And I think, Paul, you could probably give a little bit of an update of what that looks like from your perspective at stage 4.
Definitely, Shane. So I think the good thing that this diagram starts to show here is when you get to the technical design, I guess it depends on your procurement route. So it was a traditional 2-stage JCT, so a design and build project here. So effectively, the contractor takes on design liability as well. So the design's not complete in its entirety. So you bid and get involved in the project when the design is like partially complete. Then the designers, in this instance, were novated across to the contractor. So effectively, they used to work for the client. Then they come across and work for the contractor. We complete the design, and then we construct the design during stage 5. So if we go on to the next slide, please, Shane. So we were involved, when we first got involved was at a bid. So we were invited to tender the project for the university. So we got what's known as the invitation to tender, the ITT pack, that was sent to Laing. So the pack will have various questions covering various topics from methodology, logistics, health and safety to innovation and sustainability, etc. And then as a contractor, you need to respond to those. So the university, how they actually scored the tender response was 70% on technical and 30% on commercial, which tells us right from the outset that this is a client that is focused on quality and not necessarily cost, in which if you ever have the opportunity to go up to Oxford and look around some of their buildings, you'll see that is very much true. They produce high quality in terms of architecture, in terms of engineering, and an overall finish of the buildings at the university. So a quality focused client, which sits well with Laing O'Rourke's delivery model. And we were one of 5 contractors bidding. It was a considerable investment, I think, is one thing I'd really like to point out here. So effectively it's a 5-horse race, and each of those contractors invest a considerable amount of money into the cost of putting together a bid team, putting together bid material to submit. So we spent within over 6 figures on bidding this project, and for us it was great that we were actually successful and won the project, but for someone else it would have been a bitter pill to swallow.
And would I be right in saying, Paul, so some of the animated stuff that we're going to come on to in a bit, I mean, that's all part of that bid, the early stage process really to support winning it. So you'll hopefully get a flavour of what that level of commitment involves as we come on to the next slides.
Exactly. So the process, there's a mid-bid interview stroke workshop where you have a mid-bid engage with the client and consultants and ask any questions that you want and then get some feedback. And then we have a final interview that goes on, and then we were successful. And so what that kicked off is, in terms of a 2-stage bid, is the first stage of the bid is the pre-contractual services agreement, or the PCSA for short. So that was a 6-month period that is really used to reduce risk on a project. It's where, as a contractor, we can get involved, we can build, or we can bring our buildability expertise to the table. We can start looking at design, methodology, how we're going to build the building, program and cost, and then offer the client certainty. And at the end of the PCSA period, we had to give a fixed lump sum price. So basically, do not exceed price, and it's the price that we're guaranteed we're going to build the project for. So we're taking all of the risk. If it costs more than that, it's our risk. Well, there was some shared risk on us, actually, thinking about it. So we take the majority of the risk. The main risk highlighted at this stage during the PCSA, so this would have been it would have been in 2018, so kind of third quarter 2018, and the thing that was on the horizon was Brexit. So there was a lot of back and forth on how we were going to deal with the risk of Brexit with the university, and then we came to an agreement that the university would actually take the risks on any currency fluctuation, but as a contractor, Laing O'Rourke took the risks on any delay to manufacture or delays at the port due to components to actually construct the project. We move on to the next slide.
Yeah, no worries. And I would just add that that's also a good example of the kind of collaboration that was evident, I think, all the way through the process from all sides. That kind of pragmatic approach to troubleshooting and overcoming these problems.
It definitely helped the fact this was probably the 11th building that Laing O'Rourke had built in collaboration with the university. The previous building around the corner that we built had both Hoare Lea and Hawkins Brown working on it as well. So we had an established relationship.
I was going to say on that one, actually, I'm sure some of the audience would have been familiar. So at the Beecroft building, which I understand there was an integrated seminar, kind of integrated building design seminar previously. It was one of the previous kind of sessions. So maybe some of you will recognize that building as well.
Brilliant. In terms of a project overview, just a few facts and figures for those who like this sort of stuff. So Shane kind of gave an overview of the majority of this before. So in terms of, you know, the overall, it was a new building. It was an extension onto an existing building that Laing actually built back in 2008. So in a sense, we were coming back to complete the project that we first started. So research laboratories. The client was Oxford University Fixed Asset Limited. And then, as noted before, the former contract was a JCT Design and Build in 2016. Construction value down to the pound was 72,995,905. And then in terms of, you think about the different components of the cost, effectively in terms of mechanical, electrical and public health, MEP for short, value was around about 28 million. And then in terms of the substructure and the superstructure, that added up to around 11 million pounds worth of cost there. If you move on to the next slide, please, Shane. So when it came to doing a review of the design and putting together a construction program, effectively as a contractor, we work with two programs. There's the program that we actually get into contract on, which is what we call our construction program, and then there's our target program, where we will always try to better that program to buy float into the time that we have, which is of benefit. Usually, if you finish early, you can negotiate better terms with the client. It reduces your cost as a contractor because you're in and out earlier, and then having float's always a positive thing. So anything unseen, unplanned, you've got some time there to account for it. So you can see there our actual contract construction program was 109 weeks, but our program to build was 105 weeks, which was great because something massive landed right in between, which I think nobody could have predicted. If you go on to the next slide, please, Shane.
Indeed, absolutely.
COVID-19. So March 2020, there was a global pandemic that started, that had major implications for the whole world. And not the least the construction industry. Laing O'Rourke, we've got several, I think around the region of 20 construction programs operating simultaneously. And I think around 25% of our construction jobs just halted to a grind. Fortunately, Biochem was not one of those. So we got at the vanguard, at the front, put appropriate measures into place, and really managed that risk. I think we were quite fortunate in terms of where we were when COVID landed. So we were quite well progressed in the construction. That was due to the way we built the building, which Shane mentioned before about DFMA.
I think, Paul, it's also to the credit of our respective IT departments that we did continue to work well. And maybe one of the illuminating things for me is that I didn't really have to go to site anywhere near as often, and it still worked completely well. And if there were things that I needed to look at on site, either photos were sent to me, or I was shown videos of things. And it was only maybe once a month I would actually drive down to site during the pandemic, but it didn't really feel as if it was a problem.
Yeah, and that's a really good example, Alex, of how we were flexible, and as Alex said, I guess the IT departments, etc., helped with how we actually managed the process and mitigated site or risk on site. A few things that we did in terms including to remote working was your typical, so hand sanitization. We had a one-way system around site, and it was just a lot more onerous in terms of how we approached the build.
Excellent. So I think next up we have something a bit more interactive. So you okay? Yeah, if I jump the video up, hopefully, is that visible?
Yeah.
Yeah, right. I should.
This is just a short video. So as Shane said before, we put this video together during our bid to explain to the client exactly how we would go about constructing the project. As you can see, it was a really tight site, and we had to think heavily about logistics and how we would move things around the actual project. We've got a video freeze moment. It's always the problem when you try to do too much with technology during a presentation. But effectively, we had to think heavily about logistics actually on the site, about the separation of pedestrians and people from our vehicle movements. So at peak, we had over 100 wagons a day moving in and around. So these were controlled via gates and via traffic management system called Force that we use. And the challenging thing is on the hour, every hour, you have a lot of people moving around site. So what you're seeing now is the formation of the substructure. So we did secant piled walls. So those were the pile units. And then we started to excavate down to do the 2 levels dig. And then we also had to do some works within phase 1 to actually allow us to remove sheet piles on the interface and then connect the 2 buildings together as the build went on. So there were some enabling works that we had to do in phase 1 as we were going down and doing the reduced level dig. When we got down to the basement level, we then poured a big raft slab, which is 1,200 millimeters deep. And then we started to build up from there with the superstructure. So it's looking at the cranes and hoists that were used across the project to enable us to build. It shows 2 tower cranes there. We actually did it with 1 tower crane. And then we built the building using off-site manufactured components. So off-site manufactured structural slabs and off-site manufactured columns. This was a temporary fire escape from phase 1 that had to be installed as a part of the build as we were going up. So here you're seeing the lattice slabs, they're called, going into place, and then also the columns. We built the steel structure of the plant room, and then we also put on the facade. And then within the building, there were miles and miles of MEP services, which were also delivered off-site, manufactured, delivered to site, and then installed into their final position, kind of pre-commissioned, ready to go for the commissioning, where we would go through, fill all of the systems, and test that they're operating correctly in line with the building management system. Brilliant.
Oh, sorry. Excellent. Yeah. So we'll move on to the next one, which I think give you a break, Paul. I'll pick this bit up. So we move on from that, which hopefully people found quite interesting. And obviously the visual aid as well. I'm certainly, as a humble mechanical engineer, I find that very fascinating on the whole civil and structural side as well. So hopefully you found the same. If we then move on to the brief, obviously it all starts with a brief. The client brief, as we touched on previously, was ultimately a lab hotel, which for all intents and purposes, they didn't fully know who was going to move into the space. They knew broadly what type of science they wanted to try and achieve, but in a nutshell, they really wanted to create a central hub within the existing science area within that part of the university, where many different groups and many different departments would come together and work in a really collaborative and kind of, effective and fostering kind of all the right bits of science together to achieve the greater outcome, as it were.
And I think that one of the things was that the university are very much of the opinion that you don't know how science is going to develop over the next 20, 30, 40, 50 years. Correct. So you have to be able to create spaces that are adaptable enough to be able to accommodate various different types of science. Otherwise, you very quickly produce an obsolete building. Yeah, so I think that was one of the other kind of key drivers behind it.
Exactly that, and it was very much recognised from the off, both with the feedback from phase 1 and obviously Hawkins Brown's experience in these areas, is that it's not just about the science, it's about how you interact as a group of users and a group of scientists, and those kind of balance spaces and the focus of the atrium and the power it brings.
But I think I think there's a general realization now that this is the kind of issues that humanity faces are so complicated and require so many different branches of science that you have to bring academics and researchers together in order to be able to answer them, basically. Yeah. And this, you can see within the form of the building, some sort of acknowledgement of that.
Yeah. So that was core to all of what we were working towards through the scheme. So that was just a brief overview on the brief. So segueing on from that, we obviously that kind of filtered down into a variety of different space typologies, which these are notionally listed here. So the first grouping, I suppose, will be a kind of more traditional wet and dry laboratory type spaces with support labs, as these are the kind of the darker and the light blue ones that Alex touched on before.
And I think lots of the work that we had to do, Hoare Lea and Hawkins Brown, particularly in the early stages, was to really nail down with the client the base level of infrastructure, be it architectural and services, that these spaces needed. So what kind of gas, what kind of water, what kind of loading can the benches take? All of those things were being nailed, so we could just repeat them throughout the various floors, albeit with certain adaptations, if allowed, for certain particular scientists and their particular scientific field.
Exactly, and also the day two consideration. So the day one absolutely as a must. Day two with limited, the adaptability angle. So how could that be scaled up rapidly or flexed laterally? All that fed into the mix. And so it's trying to balance the flexibility and adaptability that you could provide at day one with the limitations on cost, which of course every project experiences, and trying to build all that in to achieve the greatest possible outcome for what we could foresee for the building's lifetime, as it were. And I mean, certainly feedback has been that it has been generally successful in that sense. But yeah, so I'll start with these kind of space typologies. In particular, the wet and dry labs, the more general spaces, that was really key. For the next cohort, so that image there is actually just a general, I think I'm right, I think that's one of the general primary labs on a floor plate, that with a glazed view out towards the write-up zone. And then if we go to the next one, so this would be an example of a more specialist lab. So this is the Electron the Electron microscopy suite in the basement, the one that Alex described previously. Obviously, it was undergoing validation and trial testing at the present, hence we can see these kind of little perimeter electric heaters plugged in. So the equipment hadn't been moved in, but what you can see on the walls just about make it out in the distance. The view we have here is from the control room looking into the adjacent microscopy suite. You've got these large chill panels all around the perimeter of the space. And they cool the room using static, essentially the reverse of a radiator. In effect, you're absorbing heat from the air rather than rejecting it. And the idea being that this type of passive cooling solution meant that you really minimize the amount of airflow in the space, which is really, really important for these types of equipment. And then this is a mass spec example, again, unfortunately without all the equipment in, but in essence, you can see the various service connection points on the roof and on the perimeter wall zones, and yeah, just a typical finish to that type of space typology. And then the support areas outside of the lab barrier zone. So you can see the write-up, which kind of leads onto the atrium, and yeah, just kind of fairly open plan and kind of good flow to it. And then obviously the primary circulation via the atrium itself. What you can see here just about make out is that obviously this is looking from phase 2 through to phase 1. And what you don't realize is, I don't know if you can see my pointer, but just to the right there where the barrier gate's coming through, and just behind the lift shaft there, is essentially where the phase 2 line or the phase 1 line starts. And it's seamless. You simply wouldn't know if you were to walk through the building, which I think was a key client request and very much a success, I would say. One of the key successes on the project.
No, definitely one of the brief requirements was that at the end of phase 2, which was bigger than phase 1, I know that Paul described it as an extension, but it was more than just an extension, was that the building should read as a consolidated single whole. It's not to be two separate buildings. So the idea was aesthetically, you wouldn't really notice that it was a phased building, or at least that there wasn't 10 years between the two parts of the build.
Exactly that. So if I move on to the next, yeah, so just in summary, yeah, a large, big collaborative working environment. That was the ultimate outcome of the brief, which I think has been delivered upon. In terms of challenges to be overcome, obviously, as many of them Paul touched on, so we won't dwell too much, but obviously you've seen the constraints of the site, the very fact that the phase 1 building was a live building and had to remain operational, and how that interface was managed, broken through and sealed up had to be done in a really, really controlled way. So that was a huge amount of added value that the contracting team brought on, and Laing and Paul and his team, from an early stage, which was great and very much contributed to the success of the project. And then obviously with lots of early stage design challenges too. So I thought I'd just give a little flavor of that from an MEP point of view and what that looked like. So quickly run it through. So this is just to do with the ventilation strategy for the building. So we elected to go with an on-floor plan strategy for air handling units. So for the ventilation, the mechanical ventilation. So just to take you through the kind of concept design, so with some notional high-level kind of Revit information, the drawing tool we used with some sketch schematic information to support it, we were proposing a vertical manifolded system, just allowed air to move more freely amongst the building, or within the building rather. And then at stage 3, you can see how that evolved. So more detail added within the Revit, you can start to see the vertical stacked arrangement of the plant and the vertical headers coming together. We also approached a similar style of, we approached the kind of the IT and the electrical services in a similar fashion, where we kind of stacked them vertically adjacent to the lift, and that allowed good connectivity between floors. And yeah, so that's essentially, as core designers, that's how we build up the design on the run up to stage 4. And by the time we hit stage 4, what you're seeing here now is where, obviously this is the plant room, but only showing the builder's work information. So the coordination of the services and how that aligns with the structure, the detail of the pipework and the risers and how all that comes together. It forms the basis of what Laing O'Rourke and or the contracting team would then have to pick up, price, and adopt, as it were, before they progress to the kind of fully coordinated working drawings, which then get used as the basis for installation on site. And then the construction-based challenges, obviously, yeah, kind of an order of magnitude on from that again.
Yeah, and I think it really is an extension of the same thing, really. So, you know, as the project develops and you get the detail developing, so the construction is effectively just bringing to life the design, isn't it? So some of the challenges that Shane mentioned before, we had particular challenges around the interfaces between phase 1 and phase 2, differential movement between the two different structures. So phase 2 was being built as a concrete frame, whereas phase 1 was built as a steel structure. And then also the connection of an existing basement box that we were effectively plugging onto an existing basement box. And you can do a bit of research into a C-compiled wall foundation, but effectively you get male and female piles that you kind of intertwine the piles in together, but in an existing building, and we couldn't quite key in the way we would typically key in if we were building the building from scratch. So when looking at these challenges, and we said, well, how are we going to go about mitigating all of these challenges around the waterproofing between the two buildings? The key thing for us was to model the hell out of it, to put it frankly. So we put a more level of detail to the model on this project, I think, ever than Laing O'Rourke has ever done on any other project. It was a new approach. It's more a standard approach now, but at the time it was really innovative. And then what you've got is the level of detail here on your slide to the left, which describes the amount of detail effectively that would be included within your building information modeling within your design. So typically you take it up to, at stage 4, up to a level of detail 3. So concrete geometry with penetrations in and around greater than 300 by 300, sometimes smaller. And then we took it further to a level of detail 4, then a level of detail 5 as well. And then when you go up to a level of detail 5, you're effectively modeling everything that you're going to build, everything that's going to be in there. So that includes all of your casting items, all of your rebar or reinforcement bars inside the concrete structure, and anything that we required to suit the manufacturing process as well. So we were manufacturing these at our these concrete elements, a number of them, at our factory up in Steatley, and then shipping these down to site and then connecting them on site and looping up bars on site and then connecting them through. So what you've got on the screen there are 2 shots from our model. So the top one shows a flying shore in terms of the temporary works detail and how that connected in with the rebar that was actually in the capping beam for the secant piles. So you can really see the level of detail that we're going through there. We understand exactly where a bolt's going to go, exactly where a rebar is. There's obviously tolerance built within that, but there was 0 clashes on site when we were building the tub or the outside basement, so the raft and the secant walls, which is a first for us as well.
I think definitely for me, this is the best application of BIM that I've seen on a building. Everybody, despite the fact that it wasn't a formal BIM level 2 project, I think the one thing that it really helps to drive, particularly if everybody is using programs such as Navisworks, is the coordination just goes to the next level, and things are flagged so much earlier now, and it's you're not coring holes everywhere. Generally, like all the big things were picked up, and that's not to say it wasn't perfect, because I'm sure there was a few things cored at the end, but generally the whole BIM thing really helped to drive the coordination.
It becomes a proactively driven exercise rather than a reactively driven one, which I think, yeah, I'd echo exactly what Alex said. Yeah.
And it was across, it was a full team effort as well. When we started to go through the fit out of the floors, and we were looking in the model for the fit out of the floors, and so you had all of the MEP services that Hoare Lea and Shane had drawn in there, but then all of the manifestations of the components on the walls where the droppers were coming, how that met with the architecture. Hawkins, Brown and Alex's team were modeling those as well, and then we were then taking literally snapshots of those models or iPads out on site and taking them to the people installing them. So we all worked as a team to create this joint up coordinated model, and that was used for construction. So yeah, definitely worked well.
Yeah, and then I think as a
sorry if I could interrupt.
Yeah.
There's just a question which I think might be a good opportunity to answer. So the question is, what was the impact of level of detail 5 on the overall program?
On the overall program, I'd say it allowed us to maintain our program and meet it. So in terms of the overall program, when we did a risk register early on, the program was one of the things that was high up on that risk register. So it was a very pacey program, and we really pushed it, and we understood that there was a risk there. There wasn't much float, and having this level of detail and I guess mitigating the opportunity for defects and faults helps us deliver on the program that we promised. But it was a very fast program, and this level of detail helped us maintain it.
And I suppose, Paul, thinking laterally on that same question, what level of extra commitment was it from your design team side? The integral, would it be expanded? The team who would have done that internally?
It would have been the expanded digital engineering team. So there was an investment in this. So we effectively paid for someone full time for a 6-month period. But in terms of when we go back and look at the outturn cost of the project and look at, it's hard to measure the things that didn't go wrong, right? So the only thing we can do is compare it to previous projects and have a look at some of the issues that they saw. And we estimated that it paid for itself more than 5 times over.
Yeah. Excellent.
Great.
So keeping on a similar theme, I suppose, Alex, this is kind of a different view of the same kind of feature, really, isn't it? From an architectural point of view, the kind of modular nature of how the construction was approached.
Yeah, and I just think this helps to explain, again, just some of the DFMA aspects of the scheme, because I think one of the things that Laing's brought to the job, and maybe was one of the factors that contributed to their success at winning the bid, was because they could bring this precast superstructure system instead of just your bog standard in situ RC, and therefore they could say to the client, we're going to use our precast system, our precast biscuit system, and therefore we can knock however many weeks off the program and therefore make it cheaper. And I think, yeah, is that right, Paul? That's fair to say?
Definitely, Alex. I think that's spot on. And it allows us to build a building faster, reduce costs and reduce labor on site as well. So from a health and safety perspective, it's significantly safer. And one thing I would mention about the initial design that comes before DFMA as well is, in terms of Alex and Shane's team, when they're completing the design, you have to complete the design with a mind to allow for DFMA, to give that level of flexibility, because there could have been decisions that were made earlier on that would have precluded the application of design for manufacture. So
absolutely, Paul. One of the things about working with DFMA like this is lots of the design has to be done up front, which brings its own stresses. But if everybody's on board with it, and if everybody's really looking to the horizon about what may be happening and incorporating that back in and helping drive the coordination, then it can work really well.
Brilliant.
Definitely. And I think the next example will probably show that, in my view, at least, really, really clearly. So if I segue into the next one. So I think this is just, obviously, as Laing, O'Rourke and Paul's team picked up our collective design, they obviously went around and assessed what areas they could use or would be potentially viable for DFMA. So these are kind of high-level service modules within the corridor zones. But this to me is these comparative pictures. We've got a couple of examples which I thought are really powerful, and they kind of really do demonstrate the segue from strategy to reality. And what you can see here on the left is the same view within the model at roof level of the chiller and the various high-level pipework and the steel frame gantry to support it, and then what that actually meant as we got to site. And so you can see the variation is very slight, and it just shows the power of BIM. And yeah,
just the variation in color, I think, Shane. I actually prefer the yellow and the and the colorful pipes.
It's not far off, yeah. And the Henry the Hoover in the background. And then another similar one is so this is a pump arrangement, so your LTHW heating and your chill water cooling pump arrangement skids. So you can see them being craned in. You can obviously see the preformed assembly. The only additional material component really is that kind of steel frame that kind of holds it all together and allows it to be packaged up and shipped on the back of a truck and then offloaded on site via crane. But you can see it drops into position and allows all the trades and control over the quality to happen off-site in a facility. Obviously getting various trades to different parts of the country and maintain the high quality is very difficult to achieve, I'd expect, from a contractor point of view. So doing that in a singular facility where the training and the right support can all be there in one place is obviously advantageous. And so this is a demonstration of reality of that. And then a further one there where the separate pump skid obviously being raised up onto the roof. And on the right-hand side, and we have another little video in a second to show you, this is a DFMA riser. So for those who maybe at the front end of the call weren't fully clear what DFMA is, this to me is the exactly what it is. In essence, you can drop all your pipework in straight away. So you go from a big empty riser on a Monday to having a more or less populated and bolted together riser on a Tuesday, which is very powerful, especially in a very urban setting.
Exactly, given the restrictions on the site. As an example, a riser like that on site would probably take somewhere in the region of 12 weeks to actually do, and it takes you an hour or two on site to actually achieve that when you drop it in.
Exactly. So I'm conscious of time, but I will quickly show you. There's a couple of videos where these are being dropped into position. First time I experienced that in all my years, which that was really fascinating. And then a separate riser, but similar kind of view just from outside. You can just see crane dropping it into position. Just innovation at its finest, I would say. So if I move on then to the next. And then this is just a general kind of completing shot. So where I showed you the early stage to concept design, moving through these kind of modular and kind of manifolded air handling unit plant rooms that were stacked. This is a view inside one of them. So one of the air handling units on the left-hand side, a further one on the right, and then a common set of vertical ductwork in the central zone here. Just to give you a flavor of what that looks like in its completed form. And then courageous collaboration. So obviously you probably gather that a lot of the success that we've been kind of advocating here has been a function of the kind of courageous collaboration that we've all come together and delivered and acted upon. And I think, this started at a very, very early stage and was, there's some very obvious stuff that you think, oh yeah, that would absolutely happen. And there's perhaps some very less obvious stuff that actually achieves some very, very tangible outcomes. And start with the stakeholder engagement, which an institution like the University of Oxford or UCL, where there's lots and lots of stakeholders, it's understanding what your client's drivers are. So if you imagine an owner occupier for the lifetime of the building as somebody like a UCL or University of Oxford would be, they will have a whole array of stakeholders from security to energy to facilities management and how the building will be managed who feed into that mix. And that's on top of the actual laboratory user on the ground. And so all of that has to be captured, all that information through a series of kind of user briefing sessions and engagement sessions. And so this is what you see here on the right is just a snapshot of Alex's scribbles from the back of one of the sessions, engaging with one of the users who has probably had a vested interest in this particular space in question.
I don't think they are my scribbles. They are the scribbles of the academic.
Of the actual academic.
Who was moving into the space. So that just gives you a flavour as to what we, the kind of commentary that we were kind of getting. Because exactly. the academics that you're dealing with, they very much know what they want. And I think you're dealing with some strong opinions. But that maybe gives you a flavour as to what we had to contend with. And that was the information that we gave them for sign-off.
And this was a bone of contention as well, especially from a contractual perspective, because effectively Hawkins, Brown and Alex's team went through all of this trouble of producing all of these room loaded drawings, and we had room data sheets, and they went to the client for a final tick, and they came back with all of these comments just as we were trying to get into contract, which led to a massive variation. So we had to end up going into contract for a provisional sum and deal with all of this following. So
absolutely, very much the contractual challenges. But I think the underlying message from the early stage design point of view is that as designers, as collective designers, as an industry, it's really important that we understand what the client's drivers are, what their brief is, their aspirations for the building, and very much tailor our service to suit that and to meet those aspirations. If you were to go with a speculative developer, program and cost will be king. You go to an end user who will own or occupier for the lifetime of the building, they will see the value in spending a bit more upfront to make life easier throughout the operational lifetime. So it's getting that balance right. And I think on this one, this is a good example of where you've got stakeholder heavy engagement and somebody who's a vested interest in getting a high quality product at the end that is workable for them in terms of maintenance and operation and energy and running costs, which is obviously a key factor as well. So conscious of time as well, just move on from this. Yeah, also just something else, it does happen in other projects, but I just thought it was really powerful on this one. And I thought something, it's a theme that we're running through the whole collaboration side of it, is that on this specific project, both Hawkins Brown and Hoare Lea, some of the more junior staff integrated with the construction team. So they did secondments on site for a couple of weeks. So you see Diego there in hopping out the cab, where he was 2 weeks on site, kind of as a ductwork installer's mate, as it were, helping to get a strong sense of what the buildability challenges that the contractors face and how that can then come back and translate to what we do as early stage designers. And as you can see there, he produced a couple of internal memos which were circulated around for the benefit of others in the team, just to see his experiences. And so that level of collaboration happens. I think it happens to a reasonably good level in the industry. Certainly here in Oxford, it's quite prominent. And I just thought that's really important to share that. And I would encourage you, wherever you land in industry, that you certainly engage in where these opportunities arise and encourage it, definitely. So I think we very close to the end now. So I just thought we would just touch on what all three of us learned from the project. As like we're saying, every day is a school day. Alex, Paul, and I were working together for several years. So when you think of that, key standout one for me really was you have to develop a really strong rapport with the team. There'll be times where there'll be a lot of tension, be very stressful, and so you got to be better together. And just it's really important to have a strong rapport and get to know each other's drivers, what works well, what doesn't work well, because we will have up and down days, and that's really important that we're all swimming in the same direction. And it's about having as an industry, we want to. You want to do a good job for your client, have a bit of fun along the way, and obviously make a bit of money. That they're the three ticks in many ways. And so if we're all doing that, then we're all happy. So it's important not to lose sight of that sometimes when you're caught in the crossfire of various challenges in the heat of the moment. But yeah, so for me that was a big one. I don't know, Paul, from your perspective, or Alex, what would you?
Well, definitely from my perspective, anybody who came on board and was overly adversarial or brutally contractual, they didn't really last very long. And I think the other thing that we were subject to is a 360-degree kind of KPI scoring by the university. So we were actually, all the various different members of the team, be it client side or contractor side, were all scoring each other. And that was all being fed back to some chat within the university. And if anybody started to score particularly badly, it was flagged to the client team. So,
yeah,
and again, that worked out quite well for us and for the team generally, because everybody generally did perform.
Yeah, exactly. Yeah, so I think that's an evolutionary thing that has kind of arrived at that. It's not true happenstance, I think that, and absolutely the case. Now, I know Paul. I know quality, I think, was clear on roles and responsibilities. There's a few points we discussed previous to this that I know you're.
Yeah, just in terms of the control and quality on site, and as an industry. We're improving on this and we're getting better. So with the university, they want a high quality building. At the end of the day, they want a building that's fit for purpose and meets the function of what they first stipulated in the brief. So quality control on site, we're using new methods of delivery on that in terms of taking iPads and different technology like that and going through a quite tight inspection and test program. And I think that the main thing for me that resonates here is just around, it sounds, I guess, a bit soft, but just that whole thing around communication, transparency on actually building honesty and trust within the team and doing what's best for the project. So as organizations, as Shane said, we're all trying to make money as well. So the bottom line can't be neglected, if you would, in the contractual arrangements. Otherwise, we wouldn't be here as organizations. But ultimately, we need to think about what's best for the project, regardless sometimes of what our own individual aspirations or agendas, sounds like the wrong word, but aspirations are, and really collectively come together and think, how can we deliver the best project that we can for our client?
Excellent. Perfect. And then I think that's it really. So yeah, that's in a nutshell, that's our overview of biochemistry phase 2, which is now being kind of taken on by the Kavli Institute, which obviously, as the statement says there, will be derived from a whole range of different scientific and engineering activities into the future. So thank you all for listening. I'm just going to, sorry, Paul, go for it.
One thing, Shane, and Alex, if you wouldn't mind, and it just quickly covering in terms of the building, how phase 1 was actually used to support the development of the COVID vaccine.
Well, I just think there were definitely some parts of the building that helped to do some of the secondary work. I don't think they were actually generating the vaccine on site, but there are all sorts of science that are being done within the biochemistry building that are not just for others, it's for us, because they're looking at the proteins that cause dementia, and there's all sorts of other science that are looking at various kind of human conditions and illnesses that hopefully they're going to cure. And so, yeah, you could see this building as not only an investment for everybody, but also maybe even for yourself. Yeah, absolutely. Yeah, I'd agree with all that. Yeah, so I think that's from our side. So yeah, I think we can probably revert to the Q&A.
Yes, you have a few questions. Thank you for the excellent presentation, which was truly inspirational. I'll ask you, I'll try and combine a couple of questions just to save time. So one of them is what environmental factors were considered when designing and constructing the building? And there's a related question on whether the environmental control strategy in phase 2 was different from phase 1, and what was the reason behind the change?
Do you want to go at that one, Shane?
I can certainly I can have a crack at the second part of it, if that makes sense, with the environmental control strategy within phase 2. So I would say in principle, the broad strokes are similar. So if we take a typical lab space, the heating and cooling is managed via LTHW and chilled water. So plant and then fan coil units at high level concealed within the ceiling void in each of those areas. Air changes in the labs, I think we were circa 6 air changes an hour as a baseline, which I think is similar to phase 1, but in terms of how that air is derived, is using central air handling unit plant, but obviously set up in a different way. So in phase 1, they've got individual air handling units per zone. So lots of them kind of dotted around the building. What we decided to do was pull them all together as that kind of isometric view showed and have them stacked. And part of the reason for that was when they all plug into a common vertical header, you can move the air around the building in a more flexible way. So if, let's say on day, year 4, they decided we want to put a wet chemistry lab on the second floor, 20 fume cupboards, we need 15 air changes an hour. And you then realize, well, actually the rest of the building, we're not using so much of the air, so you can shunt around the building more readily. And then second to that is, I won't get into detail into the weeds of the fan laws, but essentially if you have all your air handling units running at a lower speed or together rather than 1 or 2 running at a higher velocity or higher airflow, the amount of fan power energy you need and consequently electrical energy you need is a magnitude away from what you would have if you'd done them as individual zone units. Now there's extra complications with that, but in the rounds, we felt it was a really ambitious and I think appropriate solution, which is what we've aimed for. Now we're also in parallel doing a little comparison study to see how phase 1 and phase 2 are operating. One of my colleagues here in the office who's doing his master's actually, and it's one of his thesis topics. So hopefully we'll find the outcome of that. But yeah, sorry, I went a little bit off piece there on that topic, but hopefully answered the question.
Yes. Do you have any more comments or anyone else on the environmental factors considered?
So in terms of the environmental factors considered, and I guess at a design phase, again, Shane, it'd be good to talk to this, but I know we, in terms of the energy assessment method that was applied to the project, it was BREEAM, so the British Research Establishment, I believe. Energy assessment method was applied to the project, and I think we got BREEAM good in the end.
Yeah, I think that was a function though of, so the way I don't want to speak for the entire client's ambitions, but certainly in Oxford, they put a lot of value in tangible elements of the sustainability strategy that they can see. They're not pushing to have, let's say, BREEAM Excellent, or certainly at this point. I mean, obviously the world has moved on since this is a few years ago now, but so something like BREEAM Excellent would have carried with a premium and price that they would say, no, we'd rather we spend it in a different way that achieves more or less the same outcome that they get the benefit from, even if that means they only achieve good or very good. But basically they what's the word I'm looking for?
I think
they
what
do
they're
a
doing
tailored solution.
Is they weight. They definitely get some BREEAM credits, but they weight it towards the BREEAM credits that involve
exactly
they're the big ticks. They're the big environmental ticks, whereas the other stuff that is more to do with, say, well-being or kind of ensuring that you put fountains in, like water fountains and those kind of things, they maybe don't put so much emphasis on those ones. So I think they may not get the big very good or excellent, but they definitely get the right credits. And I give them, I think that's the right thing to do. Otherwise you end up spending a lot of money on things that maybe aren't that important.
Absolutely that. Yeah. A sustainability roadmap that suits their requirements, not necessarily what, ticks the box, as it were, to achieve the accreditation.
Great.
Yep. So,
and next question was, did the prefabrication of the slabs had an impact on embodied carbon?
The honest answer to that is I don't know. And I know it's a question that's raged in my office as to whether DFMA does generate less carbon, particularly
I would say it has to. Sorry.
Yeah, well, I think I don't know what the answer to that is, but I know it's a question that's been raised in my office, and people have argued about it as to whether DFMA, in particularly with regards to concrete frames, whether it does actually reduce carbon or whether it's just carbon neutral.
I think it depends on the typology. It's something we're actually currently going through at the moment on the humanities building for the university. So creating the concrete components inside the factory, there are things that you can do inside the factory to reduce your embodied carbon, such as use renewable energies to actually heat and cure and things like that. But the main thing that people do to reduce carbon from concrete is generally using cement replacement. So, but given precast, there's a limit on how much cement replacement you can use in the traditional GBBS perspective. But we're also looking at innovations of if you can use different things. So rather than using steel for your rebar, is there fiber-based materials, etc., that you can use? So I think it depends on the design and the applications of the concrete. But embodied carbon within DFMA components can be good.
And I think it just depends where your precast components are coming from.
Indeed.
Yeah.
Exactly. Yeah. And I know there's a trend as well towards exploring the recycled concrete angle, or certainly a portion of it. So it's very much, I think, even since biochem, I think the industry's moved on a notch in terms of the focus on embodied carbon and the entire source from where it's first derived to how it then be disposed at the end of life. So all of that, I think, is in the short 3 or 4 years since we were having those discussions, actually has really moved on a lot, which is it's impressive, I think, as an industry.
Mm-hmm. Great. Next question was, how did the lab hotel approach and the required flexibility impact any aspirations for net zero or Paris-proof energy targets, particularly when considering the wide range of lab equipment that go into these spaces?
I
think that's an excellent question. So I think we used a lot of data analysis, not to, if you want to call, over-engineer. So we had an existing phase 1 building, which had amassed at that point at least 10 years worth of tangible data. And we used that in a very considered way and with the right buy-in from the university and their stakeholders, not to over-engineer and to use that data in the right way. And so that meant we had systems that were operating in an efficient manner, not oversized. The simple example I give is like trying to drive around in your car in traffic in 3rd gear the whole time. It's not the right gear for driving in traffic, but you've oversized it to make sure you can consider some future scenario. And so we didn't. We tried to tailor it as best we could. And so through those measures I mentioned, certainly on the central building energy side, like the air handling unit plant, we did a similar thing with the chillers. We kind of had a cascade and series of them. We utilized what capacity we had spare in phase 1. We also have an extensive network of monitoring in terms of energy metering at an individual lab base, and also where there's a significant power source. I think we aim for something like 50 kilowatts as a figure, and anything less than that we had individual metering towards, probably more honest than that. and I think all that kind of got digested into a predicted energy modeling using TM54 analysis. So one of our sustainability team kind of did that early stage analysis that allows what we predicted the space usage to be, albeit with the caveat, we were doing it not fully knowing at that time who's going to be moving in, but we have amended it now that we know who's going to move in. And that's going to then be compared against the actual. So there is a post-occupancy analysis and performance optimization process that's happening. It's going to run over a series of years to make sure that what we thought it might do is actually going to do. And on the way there, we're going to fine tune things as they need adjusting. So it's and what might have been, again, that was probably very revolutionary 5 years ago, is becoming the norm. And it needs to be, really, given the focus on where we are and climate change. So yeah, I mean, and I would say the university, and I know the UCL team in a similar vein are very, very ambitious and on it in that sense, in trying to make sure that we're across the obvious things we can to save energy and do right by people and planet.
Excellent, thanks. Well, we're now at 2 o'clock. We do have a few more questions. So I'm not sure how you would like to proceed. If you would,
I'm flexible. I'm more than happy to hang on. I appreciate others may have
yes,
classes and lessons and lectures, etc., or commitments that they need to kind of move on to. But for those that don't and wish to stay on, I know Alex and Paul, whether you guys are free to hang on for a bit.
I think Paul's gone.
Oh,
but
he's gone, is he? Yeah.
Yeah. Paul's
dropped out.
Okay, so let's give it 5 more minutes maybe to try and answer the last few questions, if that's that's okay. So one question that comes from the smart buildings and digital engineering students: how did you deal with the interfaces between the services in phase 1 and phase 2?
That's a really good question. So fortuitously, I mean, in industry, I've worked on lots of buildings, lots of very old buildings from 1950s and 1960s. And so you're reliant on whatever record drawings are available at that time. And often there isn't a great picture of what's maybe evolved over time. But fortuitously, this building being only circa 10 years old in phase 1, we'd really, really good record information that allowed us to identify where those interface points were. And as I touched on before, there was really good energy metering data that had been logging. So we got to see how the phase 1 building's energy profile was working. So where we plugged in, we capitalized on what spare capacity there was. We identified those early in stage 2, the key service interfaces, including the process ones. So things like central compressed air systems and laboratory gases, we were able to kind of plug in and extend from them. So that was essentially how we went about that. There were at the interface line, there were some things that we had to remove from phase 1 just through the architectural changes that were happening. So certain ventilation units we ended up having to remove and incorporate into the phase 2 design and then backfeed, if that makes sense. But that was just through more kind of the physical site constraints rather than capacities. And then there were other things, I suppose, if you move it up a level to not just systems, but space functions. So things like the glass wash and media prep, which is where all your laboratory, your equivalent of a dishwasher for the labs on a large scale. So, and your media prep, obviously the tissue culture side of it. So all of that that happened in phase 1 was back in the day sized for accommodating a building about the size of phase 1. So all that got migrated to the phase 2 building, such that we built a glass wash and media prep facility and a central services facility that could cater for the complete phase 1 and 2 building combined. And then the phase 1 areas were decommissioned and are currently being repurposed for actual laboratory use rather than kind of support function. And so, yeah, so I would say it extended between both services and architecture and space topology. That was how we kind of broached that.
Great, thanks. So next question, given that such a thorough BIM model was developed for the project, will this be taken forward to create a full digital twin for ongoing optimization? I'm not sure if that was directed to Paul.
I think, I suppose that it's a good question. It's a really good question. I would say that the amount of modifications that will hopefully take place in the building, or hopefully won't take place in the building for the foreseeable future, is that if we got it right, there won't be a huge amount of change. Now, the reality is there's always some change. Alex and I will happily admit, in level 3 in phase 2 building, they're potentially looking at some modifications there, which we designed in back in the day to enable that to expand. But at the time, they weren't quite sure if they needed. So we just allowed soft spots in the slab, space considerations in the plant room. And so it's looking like they're going to maybe explore that and actually realize it. So there will always be change. And so having a very detailed and accurate BIM model to be able to identify where those soft spots are, where to avoid, where we can use, and obviously where all those key service interface points are, is really powerful. And so we'll, in any work we do in the building, we'll certainly be picking that model up and trying to adapt it and keep it live and current. Because that to me is that's the challenge you have, is that over time, if people don't do that, if they do small ad hoc local changes, the model falls behind, and then its value starts to diminish. Now it'll still be, I think it's still going to have a lot of value for a long time, and hopefully we can keep it in shape, as it were. But yeah, that's the value we would see.
Okay, great. So the 5 minutes is up. So again, I would like to thank you for the presentation, which was truly excellent. To our attendees, this has been recorded and will be on YouTube soon. And yeah, I hope everyone has enjoyed it. And thank you for joining us.
Yeah, no, thank you for listening. Hopefully it was enjoyable and engaging. But yeah, have a lovely afternoon.
Thank you very much.
Cheers, everyone.
Excellent.